Hello, and thanks for being here. Today we're going to continue our discussion of inferential statistics with proportions. The last time we met, we covered the first three items on this list, thinking about one-sample proportions, and today we're going to focus on two-sample proportions. So we'll compare proportions obtained from two groups, and I'll introduce the pooled sample proportion as a strategy to implement a two-sample hypothesis test to assess the difference of proportions between two groups. So recall that a sample proportion is a special case of the sample mean, and again, we can construct confidence intervals and do one sample and two sample hypothesis testing with proportions just as we can with interval ratio variables, but we need to take some special considerations into account. And so today we're going to be focusing on proportions for large independent samples, and I'll be using the notation that you can see in this table below, where P sub 1 and P sub 2 represent the unknown population proportions, N sub 1 and N sub 2 represent the sample sizes from our observed samples, and P hat sub 1 and P hat sub 2 are the sample proportions that we observed that are going to stand in as our estimates for the parameters in the population. And so when we're comparing two proportions, or asking whether two proportions are equal to one another, we're going to start off with looking at confidence intervals and hypothesis tests as a strategy to estimate whether there are differences between two groups at the population level, or whether two groups have similar distributions on the proportion of some attribute. So if the unknown difference, if the difference for those unknown population parameters is P sub 1 minus P sub 2, we'll estimate that from our sample proportions, the difference between P hat sub 1 and P hat sub 2. And so, as you might expect, we're going to need a standard error of that difference in order to account for the uncertainty that we're dealing with as a result of using sample statistics to estimate population parameters. So to calculate the standard error of the difference of proportions, we're just going to use the sample variance from each independent sample. And so this is the same logic that we used when we calculated the standard error of the difference for interval ratio variables. It's just that the information that's going into the right-hand side of this equation is a bit different from what we used with interval ratio variables. So the numerator here in each side of this equation is the observed proportion of people who have experienced some event or who have some trait in sample 1 multiplied by the complement to that, 1 minus P hat for group 1, divided by the sample size for group 1. And then we calculate the same figure for subsample 2 and add those together. And that's going to give us an estimate of the variance of the difference in proportions between our two groups. And so that's the variance, but we need to get this to a standard error. And so we do that simply by taking the square root of that sum that we just calculated. So this should look fairly familiar. We have calculated the standard error of the proportions for an overall group or an overall sample. We did that the last time we met, and so here we're just modifying this to look at the difference in proportions between two groups. And so we can use the value of that standard error to, for example, calculate a confidence interval for the magnitude of the difference in proportions between group 1 and group 2. And in this particular example, we're looking at the 95% confidence interval. So I'm using a value of 1.96 as the critical value. And again, as I noted a couple of slides ago, we're thinking about large samples here, and so I'm able to use the value of 1.96 from the z distribution to mark the 95% confidence interval. So we can think about a fairly simple example where a university financial aid office wants to know whether there are systematic differences by gender in the probability that a student will be employed during the summer. And so they ask 797 men, and 732 women, whether they were employed during the previous summer. And these proportions will become an estimate of the population parameter for these statistics to allow them to estimate the probability that future cohorts will be employed in the summer, and they can consider these differences by students' gender. So, and we can construct a 99% confidence interval around the difference in proportions employed for men and women. And the question here, again, is whether at the population level, these two groups are similar or whether there is systematic difference so that you can improve your estimates of the probability that a student will work when you know whether that student is male or female. And again, we're just relying on a two-category measure of sex to answer this question. So from the information that we have available, we can calculate three statistics. First, the observed proportion of men who were employed in last summer is 0.9. For women, it's 0.81. And the difference between those two is 0.09. So to calculate the 99% confidence interval, we simply need to calculate the standard error of the difference. So that's reflected in the value under the square root sign inside of the parentheses. When we multiply that standard error by 2.58, the critical value associated with the 99% confidence interval, we get a value of 0.046. And so we can subtract that value and add that value to our point estimate of the difference in proportions between these two groups, and we get a range from 0.04 to 0.14. So we're 99% confident that the true population proportion falls somewhere between 0.04 and 0.14. And of note, this range does not include 0, so we can conclude that there is a true difference in the population between male and female students who are employed. So that's thinking about the confidence interval, and now we can think about turning to a significance test or a hypothesis test to evaluate the null hypothesis, in this case, that there is no difference between these two groups at the population level. So I'm setting this up as a two-sided hypothesis test. So the null hypothesis is the difference at the population level in the proportion of men and the proportion of women who were employed the previous summer is equal to 0, that there is no difference. And again, I'm using the letter P with no hat over it because we're thinking about the population parameters, the true unobserved values at the population level. And the alternative hypothesis is simply the mutually exclusive and exhaustive alternative to the null hypothesis, that the difference between these two groups is not equal to 0. And we're not considering here whether men or women are less likely or more likely to work compared to one another. We're just evaluating whether there's a difference between the two groups. And so the way we set up this test is going to look very familiar by this point. The test statistic that we're going to obtain, in the numerator, we have our observed difference between the two groups, and we subtract from that the stated value of the difference in the null hypothesis, and we divide by the standard error, in this case, the standard error of the difference of proportions. So you can see the value of how we're going to estimate the value of z shown on the bottom of the slide. So once again, just as we did with the one sample significance test when we were thinking about proportions the last time we met, we're going to use the standard error of the null hypothesis and not the standard error of the observed group difference. So this is distinct from the information that we just used to calculate this, the confidence interval for the difference in proportions. So because the null hypothesis implies that men's and women's proportions of students employed are equal, we're going to find the pooled estimate of the proportion. And this is the overall proportion for the two groups. And so if two groups experience an event or an outcome, so having been employed, if they experience that in equal proportion, then the overall mean proportion describes both of those groups equally well. And so that's the claim that we're evaluating in our significance test. So to get to that standard error of the sample proportion, we first have to calculate the pooled estimate of the standard proportion. And so to do that, it's like calculating a weighted average of the proportions for the two groups. So you can see here that we're taking each subgroup's proportion and multiplying by the respective sample sizes in the numerator, adding those values together, and then dividing by the total sample size. And that reduces to the count, the number of events observed in group 1 and group 2, so the number of students who are employed in the previous summer among men and among women. We sum those together and divide by those two sample sizes, and that gives us the pooled estimate of the sample proportion. And so when we have that value, the pooled sample proportion, then we can calculate the standard error for the null hypothesis. And so the information in the standard error looks a little different from what we just saw when we were calculating the confidence interval. So we can focus on the information in the bottom half of this equation, focusing on the information below the square root sign. So you can see that on each side of that addition operator, the information in the numerator is the same. It's that sample proportion multiplied by 1 minus the value of the sample proportion. And those products are divided by the sample size for each group. And so that's giving you a sense of how much each group contributes to the overall variance in the pooled sample proportion. When we take the square root of that value and divide it into the observed difference between group 1 and group 2, we get our test statistic, our value of z. And so we can think about another example, turning away from the student employment question. We can think about a one-sided hypothesis test. So imagine a randomized experiment was conducted in a job training program to prepare trainees with enhanced time management skills. And in the treatment group, 100 trainees got the enhanced preparation, and in the control group, 200 trainees did not get this enhanced training. And of those in the treatment group, 40% were employed 6 months later, and in the control group, only 30% were employed. So we can calculate a p-value for the null hypothesis of no difference between the treatment and control groups against a one-sided alternative that employment was higher in the treatment group. And again, we're setting this up as a one-sided hypothesis test because you can imagine that the people who developed this training are only interested in knowing whether the training had a positive effect in terms of increasing people's probability of being employed 6 months later. If people were less likely to be employed, or if they were equally likely to be employed compared to the control group, then probably the training program would not be considered successful. So now we can calculate the significance test for the difference between the two proportions for these two groups, the treatment and control group. So the pooled proportion is simply the overall proportion of people who are employed 6 months later. So this is a weighted average from these two groups of different sizes, and that value is 0.33. So overall, out of 300 people, 1/3 of them were employed 6 months later. And then we can evaluate the test statistic associated with this hypothesis test. So we're calculating a value of z, where in the numerator we had the difference between the treatment group and the control group. So that's going to give us a value of 0.10. And we divide that difference by the standard error associated with the null hypothesis. That's calculated here, and you can see that the value we arrive at is 0.0577. So when we take the ratio between the difference in proportions and the standard error, we get a value of 1.73. And the probability associated with that value on the normal distribution is 0.0416. So that means that the values of z above that point on the normal distribution occupy only 4.16% of all area under the standard normal distribution. And the probability of obtaining the observed difference of 0.10, if in fact there is no group difference in the population, is 0.0416. And so at the 95% confidence level, we would reject the null hypothesis for this one-sided hypothesis test, because you may recall that the value of z, the critical value of z associated with a one-sided hypothesis test when we're dealing with large samples, Well, it's going to be plus or minus 1.65, depending on what the alternative hypothesis states. In this case, we were looking for a positive difference between the treatment and control groups. So our critical value would be a positive 1.65. And then if the value of z that we obtain is greater than that, then we would reject the null hypothesis. And so that's what has happened here. At the 95% confidence level, we can conclude that the training was effective in increasing employment rates at the population level. Everything that we've just done by hand, we can also do in Stata. So we can obtain a confidence interval for the difference proportions and also perform significance tests using the PR test I command. So again, that I refers to an immediate test, with something that we can do just by providing Stata with some information about the number of observations that we have in our sample and observed proportions. So we don't need to actually have a data set read into Stata in order to get these estimates. And so and PR test is referring to a test of the difference in proportions. So here, the hashtag obs1 and hashtag obs2 are describing the number of observations in each group, and then p-hat1 and p-hat2 are the observed proportions in each group. And then I've also added on here a comma after p-hat2, and then where we can specify the significance level that we want to do our test at. If you don't include that, then by default, Stata will give you 95% confidence intervals. So go back to our example of the university students and their summer employment proportions. I've plugged in the number of men and the number of women and their respective proportions up here at the top, and then specified a 99% confidence level. And so in the red box down here, we can see what the 99% confidence interval is. And we see that observed difference of 0.09, the calculated standard error of about 0.018, and using that value to calculate a 99% confidence interval, we can see that at the 99% confidence interval, we expect that the true population proportion is somewhere between 0.04 and about 0.14, which is what we saw earlier when we calculated this by hand. Now thinking about the job training example, where we had 1 people in the treatment group who received enhanced job training, and 40% of them were employed 6 months later. And then we have 200 people in the control group who did not get the enhanced training, and 30% of them were employed 6 months later. That information is summarized up at the top here. And here I have not specified any significance level, so we're going to be looking at a 95% confidence interval and conducting this hypothesis test at the 0.05 level of significance. And so we can look down at the information in the red box here to get a sense of the conclusion we should draw about whether the alternative hypothesis is valid in a one-sided hypothesis test. And so we get the same value of z as what we saw in the slides a moment before. The value of z is 1.73, and the probability associated, the probability above that we would observe at least that value or something larger under the conditions where there is truly no difference in proportions between the 2 groups at the population level, is 0.0416. And so again, we would reject the null hypothesis at the 95% confidence level for a one-sided hypothesis test on this question. This is just to show you that we could do the same thing in Stata. So in this case, I have actually created a data set that looks like what we have for this question about the enhanced job training program. So I have created a data set that has 300 observations where 40% of people in the experimental group are employed in 6 months later, and 30% of people in the control group were employed. And so I'm just showing you here that when we do the proportions test, which we see in the bottom half of this slide, we get the results that I just reviewed for you on the previous slide when we used the immediate version of this test. So we get the calculated value of z that I showed you and the associated conclusion from the alternative hypothesis. The more naive approach would be to simply do this as a t-test to treat our variable x, the outcome variable about whether somebody is employed, to treat that as an interval ratio variable and to just use the standard t-test command to look at group differences. And so you can see, just comparing these two tables to one another, that the point estimates, the proportions, are the same, right? Using the interval ratio method for calculating differences in average scores between two groups compared to what we get when we do this as a proportions test. But the standard errors are slightly different. They're slightly smaller when we look at when we use the proportions test. And we get slightly different values of our test statistics. So with the t-test, where we're using interval ratio variables, you're getting the t-statistic reported, and that has a probability associated with it of 0.0419. And when we do this as the proportions test, which is the correct way to do this kind of test, and you can see that we get a value of z of 0.17321, so slightly smaller than what we get from the t-test, and it has a different significance level associated with it. So this is just to show you that you can, well, certainly Stata will allow you to do a t-test rather than a proportions test on a variable that has two categories that should be treated as a proportions variable, and it's going to give you roughly similar answers, but at least in this case, we saw roughly similar answers, but the correct approach is to do the proportions test rather than to do the t-test, because the standard errors are calculated differently. Okay, so now we can think about bringing the significance testing, back to a survey data example rather than the kind of made-up examples we've been looking at so far. So here I'm going to use information from the General Social Survey that was obtained in 2 years. So I think every year since like 1975 or so, the General Social Survey, or GSS, has asked respondents to respond to a statement: a preschool child is likely to suffer if his or her mother works. And so respondents can strongly disagree, or agree or strongly agree. And so I've taken those 4 response options and just collapsed them into 2 categories: disagreement or agreement. And I'm looking at how people have responded in 2 different years, in 1977 and in 2022. So these are just, these values in each of these cells is just the number of people who are endorsing agreement or disagreement, and we have the total sample sizes at the bottom of each column. So we can set up a hypothesis test to evaluate whether attitudes are the same in 2022 as they were in 1977, or whether they are different. So I'm going to set this up as a one-sided hypothesis test, where I'm going to evaluate whether there was greater agreement with the statement about children being harmed by their mother's employment, whether there was greater support for that in 1977 than in 2022. And I'll set the alpha level at 0.01. The critical value associated with this, since it's a one-sided test, is 2.33. So we can calculate the proportions in 1977 and 2022 who agreed with this statement. You can see that in the earlier period, 67% of people agreed with the statement compared to 27% of people in 2022. And we can calculate a pooled proportion that we will use to calculate the standard error for the null hypothesis. And so that pooled proportion is 0.42. And again, that's just a weighted average of the share of people who endorse this statement that that mother's employment is harmful to preschoolers in 1977 or 2022. And so the question is whether you can get a better informed estimate of the probability that somebody agreed with this statement if you know which year they were interviewed in, or whether sort of across time people's attitudes in response to this question are constant. So we can set up our estimate of the test statistic by finding the difference between the proportions in the two periods in the numerator and then calculating the standard error of the null hypothesis in the denominator. And we get a very large value of z, right? We get a value of 25. So that tells us that there's probably extremely low probability associated with obtaining that test statistic if in fact there is no difference in the population in these during these two periods. So setting this up with all of the information we would need for a one-sided hypothesis test, the null and alternative hypotheses are stated at the top. The critical value of z at the 0.01 significance level was 2.33. We obtained a value of z that's more than 10 times larger than the critical value. So the value of z is much larger than the obtained test statistic is much larger than the critical value. And stata would return to us, for example, if we asked for the proportion of the area under the curve associated with a value of z equal to 25, would say essentially 0, that there's zero probability of observing what you did if in fact attitudes did not change between 1977 and 2022. So at the 0.01 significance level, we can reject the null hypothesis and conclude that a larger portion of adults agreed with the statement that preschool children suffer when mothers work in 1977 than in 2022. So we can also evaluate these data in stata. So we saw previously how to calculate confidence intervals. So here I'm going to use CI. This is the command for asking for confidence intervals for proportions. That we have the word proportions in the command following the CI command, and then the name of our variable. And this is the outcome or the event variable. And so here we're going to look at the proportions for this preschooler suffer variable separately for each year and then overall. So this is the tabulation that we saw earlier that's just resummarized here with these data read into stata. And then I can calculate these proportions on the preschool variable for each year, 1977 and 2022. And so you can see that the confidence interval in 1977 ranged from about 0.65 to 0.70 with the point estimate, the proportion we actually observed of 0.673 at the center of that confidence interval. And then the proportions are much lower in 2022, right? The proportions at the population level is expected to be somewhere between 0.25 and 0.28 at the 95% level of confidence. And then we can also calculate the overall proportions. So ignoring which year a person's response came from, we can see that overall for these 2 years, the true proportion at the population level ranges somewhere between about 0.41 and 0.44, with the observed proportion being 0.42. So we talked the last time we met about how to do a one sample hypothesis test with proportions. So I'm just going to revisit that for a moment here and show that in stata we can do this proportions test for a given variable and ask whether the proportion obtained from that variable is equal to the value stated in the null hypothesis. And so here we're going to treat the overall proportion observed in that last slide of about 0.42. So thinking about 1977 and 2022 when they're pooled together, the overall proportion of people endorsing this item about mother's employment was about 0.42. And so we'll treat that as the value for the null hypothesis. And then we can just ask, this is not conventional, right? But I have two alternative hypotheses set up here. One is testing first whether the proportion from one year, the earlier year, 1977, whether that is not equal to 0.424. And then I have a parallel test asking the same question from 2022. So at the population level, in these two different years we're considering, in either year, is the population proportion from that year equal to the overall value that we saw from the pooled proportion. And so I'm doing the same proportions test here. This is not an immediate proportion test, right? This is the proportions test for survey data that I have active in Stata's memory. And so I'm asking whether in a test of proportions, whether the proportion of people endorsing a particular item on this preschool question is equal to 0.424 in the year 1977. So in the earlier year. And we can see that what we actually obtain from our observed sample is a value of about 0.67 with a confidence interval that ranges from 0.65 to 0.70. And so in terms of a hypothesis test, we are going to reject the null, we will reject the null hypothesis that what we observe is equal to the value stated in the null hypothesis. We have a value of z of about, over 19. So there's very little likelihood that we would have observed in 1977 that 42% of people endorsed this particular item. So the way if that value is in fact true in the population, so probably it's the case that the true value in the population is somewhere in the range that we observe here rather than the value stated in the null hypothesis. And we can repeat that test in 2022 and come to the same conclusion, but in this case, in 2022, the proportion of people who endorsed that item was significantly less, right, about 0.27 compared to the value stated in the null hypothesis. So in both years, the 95% confidence interval for the observed proportion does not include the value stated in the null hypothesis, right? Neither of these ranges includes 0.424, and so we reject the null hypothesis in both cases. So that's thinking about one way of doing one sample hypothesis test where we've just broke the data out into its two different periods and compared those values to some stated null hypothesis. And now we're going to go back to comparing those two periods directly against each other in a two-sample hypothesis test that's going to include the confidence interval for the difference of proportion means. And so this setup is using the PR test command with the outcome variable. So this is going to be the proportion of respondents who endorsed the statement about mother's employment and preschoolers' well-being, comma, by our sorting variable. And that sorting variable is going to be the period or the year when somebody completed their interview. And we're going to do this at the 99%. We'll do this hypothesis test at the 99% confidence interval. So when we do that, this is what we saw this hand calculated before. We get a difference in between these two periods of about 0.4. And the value, and we see that the confidence, 99% confidence interval here ranges from 0.37 to about 0.45. So it does not include 0. And so that's our first indicator that at the 99% confidence level, we can be pretty confident that there is some true difference at the population level between these two periods. The value of z that is obtained is 24.91. When we did this earlier, I got a value of 25, and I think that's just because I had rounded up the proportions that we were dealing with, so this value of z is a little more precise. And the green box shows us that for this one-sided hypothesis test that we can pretty definitively reject the null hypothesis. So to recap what we've covered here today, the sample proportion, p hat, is just a special case of the sample mean x bar. And the main difference between this and the interval ratio variables that we worked with earlier is that we need to calculate the standard error for the proportions a bit differently than we calculated population mean, the standard error associated with population means for interval ratio variables. So here we can review how to calculate a confidence interval for some stated level of significance. And we also discussed how to test the hypothesis, a one-sample hypothesis test, so comparing the observed proportion to some value stated in the null hypothesis. This is the formula that we would use to calculate the critical value, to calculate a test statistic that we would compare against a critical value. And we also talked about how to do how to compare two proportions to each other. So, proportions for men's and women's summer employment, proportions for people in the experimental versus control group for a job training program, proportions of people endorsing a particular survey item in 2 different years. All of those things we can calculate whether the two proportions are equal to one another. And in order to do that, we have to be able to calculate the pooled proportion as well as the proportions for each of our subgroups. I just want to note that we've worked exclusively with large samples where we're calculating values of z for our test statistic under the assumptions of the standard normal distribution. So we haven't talked about working with smaller samples. So this is what you'll only be evaluated on these conditions on your problem sets and quizzes in the final exam. And that's all I have. So thanks very much for your attention, and I will see you in class.